This is the 8th and final video in a series on second year integration techniques for A-level maths. The aim of this video is to use standard derivatives provided in the formula sheet to solve integrals. So here there's just a small image of something that you'll find in the formula booklet that shows you how to differentiate tan x, sec x, cot and cosec x. But integration is the reverse of differentiation, so we can use these to solve integrals as well as differentiation, and here we'll focus on how they're used in integration. So I'll go through an example. So example 1, we have the integral of sec squared 3x dx. Looking at the formula sheet, and in particular this line, we can see that differentiating tan x leads to sec x. I'm just talking as if k is equal to 1. So integrating sec squared x will lead back to tan x. Just going to make this a bit simpler by letting u equal 3x. So du dx is equal to 3, therefore du over 3 is equal to dx. We'll see why this is useful. We now have sec squared u du over 3. This just allows for the argument inside sec squared to be simplified, and then just in that last line 1/3 has been taken out of the integral. Then we can just read off the formula sheet this line again. Integrating sec squared x or sec squared something will take us back to tan of that same thing, so we'll have 1/3 tan u plus c. Reinstate x, so 1/3 tan of 3x plus c. Okay, move on to a second example using the same sort of approach. So the second integral is tan x sec squared x dx. One part of the integral is related to another by differentiation. We know this by looking again at the highlighted line here. Tan x and sec squared x are related by differentiation. Sec squared x is the derivative of tan x. So this is related to this by differentiation. If that's the case, this goes back to one of the earlier methods, and this bit that differentiates to make the other part should be our value of u. So as tan x differentiates to sec squared x, let tan x equal sec squared x. So that was nonsense. Equal u. So du dx equals sec squared x. Therefore du upon or over sec squared x equals dx. Now we can rewrite this integral. Tan x is just written as u, sec squared x, we haven't done anything to it yet, and dx is du over sec squared x. Sec squared x and sec squared x are found top and bottom, so they cancel each other out, and we're left now with a very simple integral. The integral of u with respect to u as u squared over 2 plus c. Just need to reinstate tan x as u, right, our original substitution. Tan x squared over 2 plus c. Written in a more typical format, that would be 1/2 of tan squared x plus c. Okay, moving on to a third example. That's just a little more tricky. Example 3. The integral of sec cubed x tan x dx. This one needs to be rewritten. If it's written as sec squared x sec x tan x, as if these should explicitly be written as a product that way, instead of blending all of the sec x terms together as sec cubed x, it's broken up as sec squared x and sec x. If we look back at the set of different derivatives that we're provided with, we can see in this line, the second line, that the derivative of sec x is equal to sec x tan x. So the derivative, again if I rewrite sec x squared, so this can be viewed explicitly, the derivative of this is this. So if you differentiate sec x, you get sec x tan x. So the part that can be differentiated to the other part of the integral should be u. So let u equal sec x. Therefore du dx is equal to sec x tan x. It's coming straight from that highlighted line in the derivative part of the formula sheet. Du over sec x tan x is equal to dx, and we can rewrite this integral. So sec x squared, that's u squared, and then we haven't done anything about sec x tan x. We've swapped out dx for du over sec x tan x. Sec x tan x are found top and bottom, so they cancel. And the integral becomes u squared du, which is easier to deal with. Once integrated, that's 1/3 u cubed plus c. U was equal to sec x, 1/3 sec x cubed plus c, and then just more typically 1/3 sec cubed x plus c.